Hello viewers, hope all of you are doing great. In this video, we are going to code a neural network from scratch. We're going to write the code for this network and then we're going to train this network and then we are going to give this network a set of 2D points as input. And we would want the network to generate the reflection of all the input points with respect to the y-axis as its output. In this example, each of these orange pixels, they represent a 2D point, 2D input point to the network. And each of these blue pixels, they are the output generated by the network with respect to one of these orange pixels. Please note here, this is just a fun example that I'll be using to demonstrate the working of the network. However, the same network you can use to perform some benchmark tasks like house price prediction or handwritten character digit recognition. The main goal of this video is to write the code of a neural network from scratch so that we get a more clear understanding about the inner workings of a neural network. Before writing the code, let's see a few details about the network that we're going to code for. The number of neurons in the input layer will be 2. As I have said you, the network will be using the network to take a 2D point as input and to generate another 2D point as output. So the number of neurons in the input layer will be 2. The number of neurons in the output layer will be 2. And the number of neurons in the hidden layer, it will be NEH. In fact, you will realize when we finish writing the code, you will realize that changing the number of neurons in the input layer, in the hidden layer, and in the output layer, it will be just a matter of changing the value of some predefined variables there. Then the number of hidden layers. In this implementation, we'll be implementing the network only for one hidden layer. However, once you understand the basic concepts and how to implement one layer, then implementing more than one hidden layers will not be a difficult job. Let's now talk about the activation function. In a neural network, in general, in the hidden layers, well, we can use any nonlinear activation functions, or at least we can say that we have different options for activation functions such as ReLU, sigmoid, 10x. Obviously, they have their own advantages and disadvantages, but the main point is that all of them will work more or less. However, since we know that ReLU performs much better than sigmoid and 10h, in this implementation, we'll be using ReLU as the nonlinear activation function for layer 1. You see here in this diagram, I'm writing activation 1 for layer 1. It means that is the function. So if now in our implementation, this activation 1 function will be the the ReLU function. If someone wants to use a say for example sigmoid, in that case they have to replace the activation 1 function by the code of a sigmoid function. You will see it when we will do the implementation. Changing it from ReLU to sigmoid, it will not be very difficult. Now let's talk about the activation 2 function. See here in layer 1 we'll be using activation 1 function, which we'll be implementing for ReLU, or where we'll be implementing ReLU function. And now we are talking about activation 2 functions, that is the activation function that we use in the output layer. Now see here, in general, the activation function that we use in the output layer, that depends on the task that we are doing. In this example, we are doing regression. And for regression problem, we don't usually use ReLU or sigmoid as the activation function of the output layer. Usually, we'll be using a linear function as the activation function when we are doing regression in the output layer. And using a linear function as an activation function is same as that we are not using any activation function. Now, the point here is that I said you that we don't use ReLU or sigmoid as the activation function at the output layer when we are doing regression. Let's see why it is true. Let me give you an example. It will give you an idea like why we cannot use ReLU or sigmoid. This is the graph of the ReLU function with respect to its input. So Z is the input to the function and this y-axis represents the output of the ReLU function. You can see here for any input which is less than 0, the output is 0. The output of the ReLU function is 0. However, for any input which is greater than 0, the output of the ReLU function is same as the input. One point you note here that the output of the ReLU function is always within the range of 0 to infinity. Now let's see the graph of a sigmoid function. Here also I'm plotting the graph with respect to g and sigmoid of g. This is the input to the sigmoid function and this is the output of the y-axis is the output of the sigmoid function. You can see here that the output of the sigmoid function is within the range of 0 to 1. Now let's talk about our problem. So in our problem, suppose we give the input point as 0.5 and 0.5. What we want our network to do, we want our network to generate the reflection of the input point. So the reflection of this input point, the coordinates of the reflection of this input point will be minus 0.5 and 0.5. It means, see here, we want this QX to be minus 0.5, but ReLU cannot generate a negative output. Similarly, sigmoid also cannot generate a negative output. So for that reason, you can think like we don't usually use any activation function that bounds the output in the output layer. Usually we do not use any activation function, or in general, if you want to tell it, then we'll be saying it, okay, we use a linear activation function at the output layer when we are doing regression. Now let's talk about the cost function. Whenever we are doing a regression problem, then one very useful cost function is mean squared error cost function. In mean squared error cost function, what we do is we subtract the desired output from the generated output and we take the square of it. See here, for any given input with the current weights and the biases, the network will always generate an output. So the mean squared error says that if that output, if we subtract the desired output and we take the square of it, that will give us a measure of how far that desired output is from the generated output. And that cost actually allows the network to update its weights and biases there. But anyhow, we are not going to get into the details of those things in this video. So the main point here is that we are going to use mean squared error, which can be written like this as the cost function for our implementation. Now let's talk about the weights and the biases. We'll be training the network with one example at a time. So at any point of time, A0 will contain one specific example or one specific training example, and Y will contain the corresponding ground truth for that training example. So A0 will be a 2x1 matrix. You see here A0, you can think of it's a column vector with two components. And if you want to represent it as a matrix, then you can say that it's a 2x1 matrix. It means it has two rows and it has one column. Similarly, the size of this Y will also be a 2x1 matrix. We'll encode all the weights of layer 1 in W1 matrix, and we'll encode all the weights of layer 2 in W2 matrix. And the biases of layer 1 will be stored in B1 matrix, and the biases of layer 2 will be stored in B2 matrix. Now see here, the sizes of these matrices, you can see that it depends on the number of neurons in the input layer, in the hidden layer, and in the output layer. For example, if you see W1, the size of W1 is written here as 3x2. It means it has, why it is 3x2? Because here in this diagram, we're saying that, okay, let's say 3 neurons are there in layer 1. So that 3 is coming here, and then 2 neurons from the previous layer. So that 2 is coming here. Suppose in the hidden layer, we want to use 10 neurons. In this case, W1, size of W1 will be 10 into 2 or 10 cross 2. Similarly, if you see W2, here 2 is the number of neurons in layer 2 and 3 is the number of neurons at layer 1. So that's why size is 2 cross 3. But suppose here we have 10 neurons. In that case, the size will be 2 cross 10. I guess people got the idea. So that's how we are going to store the input, the corresponding output, the weights and the biases of the network in the program. Now, once we know all the details, then it's time for the final algorithm that we're going to actually implement. At the beginning, what we'll do is we will perform an initialization step where we'll be initializing all the weight matrices and the bias matrices to some random numbers. And once it is done, then what we'll do is we'll take one input and its corresponding output. We'll store the input in A0 and we'll store the output in Y. Then we'll be performing a forward pass or forward propagation. The main objective of forward propagation is to compute the activations at layer 1 and at layer 2. As you can see here, A1 is computed like this and A2 is computed like this. Now see here, to compute A1, we first compute the intermediate result Z's, and then that intermediate result Z we pass through the activation function, and then we get activation 1. Same thing we perform with same steps we perform when we want to compute A2. First we compute the intermediate result Z, and then we pass it through the activation function. That's what you can see here. A1 and A2 is the final thing that we want to compute, but to compute A1 and A2, first we'll be computing Z1 and Z2. These are all matrices. Once the forward propagation is done, the next step is to perform a back propagation. In back propagation, the main objective is to compute the gradient of the cost function with respect to all the biases, all the weights. See here, biases means all the biases at layer 2, all the biases at layer 1, all the weights at layer 2, all the weights at layer 1. So we want to compute the gradients of all these different components with respect to the cost function. That is how much the cost function changes when we do a small change in any of these parameters that we want to compute. That is the main goal of computing the gradients. See here, we have four matrices B2, W2, B1, and W1, and we want to compute their gradients. So basically, we have to compute DB2, DW2, DB1, and DW1. So DB2 is a matrix that represents the gradients of this B2 vector or B2 matrix. Similarly, DW2 is also a matrix that represents the gradients of this W2 matrix, and same way we have DB1 and DW1. To compute DB1, DB2, DW2, DB1, DW1, we have computed some intermediate results here like DE2, DA1, DE1. But ultimately, we have to compute these four components. Once we compute the gradient of all these different parameters, then what we do is the next step is, after computing gradient, we have to compute or we have to update the weights. And updating the weights is very straightforward. What we do is we take a constant proportion or we subtract a constant proportion of the gradients from their previous values. This constant proportion is known as the learning rate. Once we update the weights and the biases, then we go back and we take a next example, and with the new weights and biases, we perform the forward pass. Again, we compute the gradients. Again, we update the weights and biases. And this process we repeat for all the training examples. Not only that, we repeat this entire process as many times as specified by this another hyperparameter known as epoch. That's all then. This is the algorithm that we are going to implement. Okay then, let's start coding. Okay, it's time for coding then. First, let's import the libraries that we'll be using for our coding. So we'll be using NumPy library for matrix operations in general, and then we'll be using matplotlib library for plotting the graphs. So let's first import those libraries. Import NumPy as NumPy np, and then import matplotlib dot pyplot as plot say. Okay, these are the libraries that we'll be using. Then the next step is this initialization process. Here our task is to create those matrices and then initialize them with some random numbers. Let's define a specific function for this step. Let's call this function say initialize. And inside this function, we'll be creating these matrices, and then we'll be initializing them. Let's first see how do we create and how we can initialize it, okay, or how easy it is actually to do that. So let's say W1, we want to create a matrix 3 cross 2 matrix here, like that. So numpy dot random dot ran function will help us here. Here we have to specify how many rows and how many columns that we want. And let's see what this W1 looks like. Okay, so let's return this W1, and then let's call this function. Say W1 is equal to initialize, and that's all. And then we want to print, say print W1. Let's see how does this W1 look like. Now see, you can see W1 now, we are calling this initialize function, and then it is returning us a matrix 3 rows 2 columns, that you can see like here, 1 row 2 row 3 rows, and each row there are 2 columns, and the values of W1, they are within the range of 0 to 1. If you see, it is 0.75, 0.6, 0.3, 0.6, you know, they are set to some random numbers within the range of 0 to 1. If I re-execute this block of code, you can see these numbers will change. All of the dimensions are same, but the numbers are different. Okay, now that's clear, I guess, right? Now, before creating this W2, B1, and B2, let's do something with these hard-coded numbers 3 and 2. Now we know this 3 is coming, like here I'm writing W1 equal to 3 cross 2 because that many neurons, this 3 is actually the number of neurons in the hidden layer, and this 2 is actually the number of neurons in the input layer, right? So for that, instead of hard coding them, let's say whenever we call initialize function, that time itself we specify how many neurons we want in the input layer, in the hidden layer, and in the output layer. Let's do it first. So say number of neurons in input layer. So I'm calling it, say, input neuron, comma hidden neuron, comma say output neuron. These are some names that I'm giving. And when we call it, then we'll be specifying input neurons, say for example 2, hidden neurons, say for example 3, output neurons, say for example 2. And this 3 here, instead of writing 3 directly here, this number is the number of neurons in the hidden layer, and this 2 is the number of neurons in the input layer. So that's how now we can, now you see, changing the number of neurons in any layer now is very easy. We just have to specify those numbers. Automatically things will be created for us. Okay, let's see whether this block of code is right now working or not. So we want 2 cross 2 comma 3 comma 2, number of input, hidden, and output, number of neurons in input, hidden, and output layer. Okay, let's see. It should give us this W1 matrix right now. So W1 is returned to us. The same way now, creating this, if you have understood up to this point, then creating W2, B1, and B2 is damn easy, isn't it? Like this is now W1, then W2, sorry, that's W2 we want, and this is B1, and say this is B2, this is B2. Okay, and then specify the sizes properly. W1 we want in hidden into input, W2 we want output into hidden. So number of neurons in the output layer and number of neurons in the hidden layer. And then we want B1 to be number of neurons into hidden layer into 1, number of neurons in hidden layer into 1, and B2 number of neurons in the output layer, and then this is 1. That's all that we want. And at the end, what we can do is we can return everything. So we can return like W1 comma B1 comma W2 comma B2. Okay, and that's all. And we can receive them in this way: W1, B1, W2, and B2. Okay, W1 comma B1 comma W2 comma B2 is equal to initialize this, and then we can print W1. So W1, the same way we can print all of them actually. You can see that W1, this one, W1, W2, B1, and B2. So this is your W1, 3 rows, 2 column. W2 is 3 rows, 2 rows, 3 column. B1 is 3 rows, and B2 is 2 rows. So that's how we can create. Although I said you that we'll be initializing the numbers within the, with some random numbers within the, now here by default things are happening within the range of 0 to 1. But first, like from my experience, what I can tell you is that if we assign the real numbers within a range of minus 0.5 to plus 0.5, this gives you better results. So for the time being, what you do is that we are not going to initialize this weight matrix within the range of 0 to 1. Rather, we'll be initializing them within the range of minus 0.5 to plus 0.5. Okay, so for that reason, I'll be subtracting 0.5 from these numbers. You can see that. Now see, if we subtract 0.5, initially it was within the range of 0 to 1. Now we are subtracting 0.5, means it is now within the range of minus 0.5 to plus 0.5. I guess people can appreciate that point. Right now, W1 is same within the range of minus 0.5 to plus 0.5. W2 also we want to be minus 0.5 to plus 0.5. And these biases, although I said you that you can initialize them to some random numbers, in practice, these biases are usually set to 0. So we are not going to initialize them with some random numbers. Rather, what we'll be doing is we'll be initializing them with zeros. So B1 is equal to NP dot zeros. This is a useful function. Zeros is a useful function there in NumPy, where we can initialize a matrix or a with zeros there. Say here we have to specify how many rows and how many columns that we want. So the this is same as this, right? So this hidden layers, as many neurons in the hidden layer, that many rows, and one column. So same way B2 also we want to be only zeros. Okay, so only zeros. Instead of initializing them with some random numbers, we are initializing them with zeros. So B2 is not hidden, output neuron, and then 1. So let's now print these values and see. Now they are initialized to minus 0.5 to plus 0.5. Any value they can come, they can have. This is W1, this is W2, this is B1, and this is B2. Okay, B's are initialized to zeros, W's are initialized to within the range of minus 0.5 to plus 0.5. Done. Our initialization process is done. We have written a function called initialize. Now, whenever we need it, we can just call that function and we can make use of it. Okay, done. Great. Now, for the time being, I'll delete these few lines of code because anyhow we're not using them. Okay, that those lines were only for demonstration purpose. If people are okay, fine with that, right? Yes. Okay. Anyhow, we are going to get this code in GitHub and I'll be giving you the link for it. So don't need to worry about it. This is, I'm demonstrating it only for, your understanding. I'll be moving slowly so that, if people understand the concept. Now, initialization is done. Now, this step is done. Now, the next step will be our forward pass. This is an important one. And see here, these are the steps that we have to implement in our forward pass. To implement this forward propagation, let's see what are the data that this forward propagation needs. It needs W1, B1, W2, B2. Those we can get. And also it needs, see here, this A0 and A1. Out of these A0 and A1 we do not have to specify from outside because this A1 will be computed during the forward propagation itself. However, we have to specify this A0. This A0 is nothing but it is the input to the network. And okay, let's first define a function. Define forward propagation. Forward prop. You can call it anything by any name you want. And inside this, we'll be specifying all these, data. Like we'll be passing this data. We'll be specifying what is W1, what is B1, what is W2, what is B2. Along with that, we also specify what is A0. A0 is nothing but it is the input to the network. And in this example, we want our input to be two-dimensional. Okay, and then what we want is we want to compute this result first, G1, which is nothing but matrix multiplication of W1 with A0. Then we have to add these biases with it. Let's first see this particular step, and if we understand this step, then rest of the steps will make more sense. It will be easy to understand the rest of the steps. Okay, so let's first do the first step. We want this Z1 to be matrix multiplication of W1 and A0. So we'll be doing it in this way, NP dot function, and there we'll be specifying what is W1 and what is A0. So that will perform a matrix multiplication. And then let's, for the time being, return this z1. First, we'll check whether this multiplication is done properly or not. Once done, we will continue, or we'll finish this rest of the steps. Okay, done. Now return z1. Now we want to call this function, say forward propagation. Suppose we want, this is the definition, and if we want to execute this block of code, we have to call the function. Now to call this function, let's this w1 b1 w2 b2 we can directly get from by calling this initialize function. But what about this a naught? As I said, a naught is input to the network and it will come from training example. But for the time being, let's create this a naught by ourselves. So we want a naught to be a two-dimensional array. So we'll do something like this. First, we'll be declaring a list of two numbers, anything 0.5 comma 0.5. You just consider this is an input point. We want to give the input as 0.5 x coordinate, 0.5 y coordinate, and that we want to be a numpy array. So we'll be writing numpy array. That's all. It's a two-dimensional array, numpy it is. And if we want to make sure that it becomes a two-dimensional array, we can write like reshape and 2 rows 1 column. Done. That should give us, now if I print a0, it should tell us, okay, this is a two-dimensional numpy array, 2 rows 1 column. I'll print 2 rows 1 column. It's a 2 rows and 1 column. It's a matrix now, you can see that, right? Okay. Now what we want is, we want to call this this forward propagation function. So forward propagation. Before that, let's get this w1 b1 w2 b2. Is it in this order? w1 b1 w2 b2. Okay, let's get these values. Initialize. I'm just demonstrating. Okay, initialize, and then 2 comma 3 comma 2. Okay, done. And we have this w1 w2 w1 b1 w2 b2. Now we'll be passing it through this forward propagation function. Forward prop. Let's do this. And here we write g1 is equal to forward prop a0 will be passing, and then this w1 b1 w2 b2, this thing, and then we'll be printing this g1. Now that g1 should be, now let's see what this g1 should be. Now see, g1 is a matrix multiplication of w into w1 into a0. w1 is here we have defined w1 to be a 3 cross 2 matrix, and this is 3 cross 2 and this is 2 cross 1. So it will be ultimately z1 will be 3 cross 1 matrix. Okay, so g1 should be 3 cross 1, that is 3 rows should be there, 1 column should be there in g1. You can see in z1 we have 3 rows, and in each row we have 1 column. Although we are not verifying these products, but the dimensions are same. That should give you the hint that, okay, whatever this matrix multiplication we are performing, it is doing the right job. But if you want to verify these results, then you can verify it. Okay, now not only this z1 we want to compute. See here, z1, not only this matrix multiplication we want to do, along with that we have to add this b1 also. But since b1 is a 3 cross 1 matrix, you can directly add it with this. So this b1. Now it will still give you a 3 cross 1, you know, matrix as an output. The z1 will be a 3 cross 1 matrix. That's done. z1 is computed, and then from there we want to compute this a1, which is nothing but a1 is equal to activation 1, and we'll pass this z1. Now what is this activation 1 actually? As I said you, activation 1 is the activation function, non-linear activation function that we want to use in hidden layer or in our layer 1. So that, as I said, we'll be using relu. Now for these, activation 1 is nothing but it is the relu function. So we have to write the code for the relu function first. So let's first write the code for the relu function. So let me add here a block of code and let's call it a relu. So we'll be defining another function. See, we are going to write the code for activation 1, and in this case it is the relu function. So let's call it say relu, R-E-L-U. I'm just giving this name. You can give any name you want. So relu function, and what we want this relu function to take input as, we want this relu function to take the input, it will be a matrix actually. So let's call it say z. And what is this relu function? Relu, if you remember, like see here, the relu function returns 0 if the input is less than 0, and if it returns whatever it is the input if it is greater than 0. So this is the graph of relu function. Now implementing it is quite straightforward. Let's see. Here what we do is we can do something like this. We can return numpy dot maximum of 0 comma g. So whatever it is the maximum value, it will be returned. Let's first see how does this ReLU work. Okay, let's first define an array. Say for example g is equal to numpy dot array. I'm just creating a random array. Say 0 point, some numbers are bigger than 0, greater than 0, some of them are equal to 0, some of them are less than 0. So 0, say minus 0.9 comma 0.9 comma minus 0.001 comma 12. Some one random array I have created, and then what I want to do is I want to call this ReLU function, and let's store the result in X, call ReLU, and then pass this z as input, and let's print this X. Okay, so this is capital. Now let's see what this X is. Now see, our input was 0 0.20 minus 0.9 0.9 minus point something and 12. So when the number is greater than or equal to 0, it is same as the input. So 0 0.2 will come as 0 0.2, 0 will come as 0, minus 0.9 is coming as 0 because it is less than 0, so the output will be 0. 0.9 as it is, minus 0.001 is 0, and then 12 is as it is. Now you can see what this ReLU is doing. If the input is less than 0, it is returning us 0, and if the input is greater than 0, it is returning us whatever that input is. So we can pass an entire array, and this ReLU function will perform this operation on each element of the array. I hope people have now understood how does this ReLU work. It's a quite straightforward function, isn't it? So that's all then. Now what we want to do inside ReLU, this is the definition of ReLU. So we'll be passing an array here, and it will return us, like, if it is greater than 0, then the value itself. If it is less than 0, it will return us 0. Clear? Now what we want to do is we want to make use of this ReLU here. Now Z1 we have computed. This is your G1. This is our G1, and then we want to compute A1. So A1 will be equal to whatever it is. We'll be calling ReLU now. We'll be calling ReLU, and we'll pass this Z1 through this ReLU function. That's all. A1 is done. Now we can see what is A1. We'll see in A1 now all the values will be greater than 0 or equal to 0. So 0, and here next time if I execute, because of this random initialization, we might get different results every time. But every time, whatever this A1 is, all the values will be either equal to 0 or greater than 0. That point should be clear in your mind, right? Okay, fine. Now once we have computed these, this step is done. Z1 we have computed, and then A1 we will do in this way. A1. Okay, here actually we don't have to compute A1 here. We'll be computing A1 here. I'm sorry. A1 is equal to, now we'll be calling this ReLU of Z1. Okay, here itself, right? So these two steps are done. Z1 is done, A1 is done, and then what we want to do is we want to compute what is Z2. Z2 is equal to, it is same as, now we want to perform W2 and A1. So this is the step. Numpy dot we want W2 comma, first thing is multiply W2 matrix with A1 now, whatever we have computed here. Along with that, we have to add the biases B2 done, and then we have to pass it through this activation function 2. Through this activation function 2. Now what is this activation 2? Activation 1 was ReLU, we have understood it, but what about activation 2? As I said, we'll be using a linear activation function. It is same as not using any activation function. But then also, if you want to put everything in the same format, what you can do is you can define a activation 2 function. So we can call it, say for example, linear. Activation 2 is a linear function. We'll pass z, and what it will do is it will simply return you that z itself. So that's why I'm saying that it is same as not using any function. Just to put everything in the same format, I have written this activation 2 function as linear function. So here you can use it if you want. Like activation 2 now is whatever it is the output, that is z2, will be passing it through this linear function, and whatever it is, that is the output. So basically passing it through this linear, because you see what this linear function is returning us, whatever we pass as input, the same thing is it's giving us as an output. So instead of calling it like a2 equal to linear of z2, directly you could have written there a2 equal to z2. But again, I'm saying just to put everything in the same format, I wrote this extra function. But otherwise, it is for just for your understanding. Once you understand, you can skip steps like this. Okay, anyhow, we have computed z1, z2, a1, a2. Our goal was to compute, see, the goal of forward propagation is to compute the activation at different layers. Like here we had to compute a1 and a2. Those we have computed. Now let's this computation. Now after doing this computation, what we have to do is you have to actually return this value. This z1, z2, do we need them? But we might need them, so let's return everything. What is z1, what is a1, what is z2, what is a2? Okay, so these values will be returned. Now what we can do is we can check this z1 comma a1 comma z2 comma a2 forward propagation. Here I'm just doing a testing of this forward propagation function. Initialize we'll create a 2D point first, then we'll call this initialize function to get these random weights and biases, and then we'll call this forward propagation where we'll pass this random weights and bias matrix, and then also we'll pass this input, and it will return us z1, a1, z2, a2. Out of this we are interested in a1 and a2, so let's print this a1 and a2. Okay, let's print this a1 and a2. So we'll be printing a1, and this will be printing a2. A1 is the activation of layer 1, a2 is the activation of layer 2. So now see, if you remember this our initial diagram, here suppose in the hidden layer we have 3 neurons, and in the output layer suppose we have 2 neurons. In that case, we want activation 1 to be a 3 cross 1 matrix, and activation 2 be a activation 2 to be a 2 cross 1 matrix. That's the sizes should match. Okay, so let's see, we run this code and see this a1 and a2. A1 we want okay, it is showing me this error linear because I didn't execute this block of code, I guess. Okay, let's now again do it. Okay, now you see here this activation 1 is this and activation 2 is this. So that matches with our requirement, right? I mean, you can see it here. Activation 1 should be a 3 cross 1 matrix. Activation 2 should be a 2 cross 1 matrix. And if I change the number of neurons here, it should not be difficult now. You see here, if I want to say, for example, we want 10 neurons in the hidden layer, then what we'll do, this number will become 10, and as soon as this number becomes 10, a1 will be a 10 cross 1 matrix there. You see, automatically things should be taken care of. A1 is now a 10 cross 1. These are the activation values at layer 1. So if we have 10 neurons, we need 10 different values there, right? 10 neurons means 10 different activation values at this layer. And even if we have 10 neurons here, we still have 2 neurons in the output layer. So we get the result that way here. Still, A2 is 2 cross 1. Are you getting what am I trying to say you? I guess things are making sense to you now, right? So that is the forward propagation. That is the forward propagation where we have this activation 1 means we have ReLU function, and activation 2 is the linear function. So linear function. Done. Our forward propagation is done. Now it's time for the next step, and the next step is computing the gradients. Okay, let's now compute the gradients. To compute the gradients, first let's define a function. So define compute, and inside this function we want to compute these steps. Now to compute these steps we need some input also. Let's first decide what are the inputs that we have to specify. We need to specify O and Y. Now, what is this O and what is this Y? Let's see here in this diagram. This O is nothing but it is the output of the network, and the output of the network is same as the output of the last layer of the network. So here we have 2 layers. So these activation 2 will be the output of the network. And what is Y? Y is the ground truth corresponding to the input. You see, at any moment of time or at any point of time, we'll be storing one training example at A0, and the corresponding ground truth will be stored in Y, and that is this Y. See, the dimension of Y and output should be same. So here O will be A2 and Y is, let's say we have the ground truth stored somewhere in Y, so that is this Y. And also what are the inputs that we'll be needing? We'll be needing what is this Z2. Now see, Z2 is actually passed through another function activation to prime. We'll be writing the code for this function in a moment. But before that, let's first fix what are the inputs this function might take. Okay, so we need O, we need Y, we need Z2, and we need A1 transpose. So A1 will be enough. And then we need W2 transpose, so W2. And then we need G1 also. We need A0 also. Okay. Now see, once these formulas are given to us, then implementing these formulas, this is quite straightforward. But if you're curious about like how do we derive these formulas, or what are the meaning of each and every component there in these formulas, then I have a comprehensive video on the mathematics of neural network. The link of this video will be provided in the description. So if you are curious about knowing the underlying math of neural network, then that video might be useful for you. Okay. Okay, now these are the inputs we want this function to take, and then internally we want to compute these steps. Now to compute these steps, you can see here we need to write the code for activation 2 prime and here activation 1 prime. Let's first write the code for these two functions and then we'll perform these steps. Now what is this activation 2 prime function is? It is the derivative of activation 2 function. So activation 2 function, we have used linear function. So what is the derivative of a linear function? So we'll be writing it, say, we'll be calling it, say, for example, linear prime. Okay. So linear prime it will take, say, some input z, and what it will return us? It will return us 1. Now, how do I know that how do I know 1 has to be returned? Because you see here, the derivative of a linear function is 1. I mean, it is asking you what is the, okay, let me write it here. So a linear function, the plotting of a linear function will look something like this. So this is input x and this is the output y of the function. So linear means whatever it is x, the x is proportional to y, and if x is equal to y, then it will go through this origin. Now the point here is, what is the derivative of a linear function? So if you ask like dx, basically it is asking you what is the rate of change of this function y with respect to x. But we know what is y. Y is equal to x, or y is equal to some constant multiplication of x. So basically d, some constant c into x and dx. So this is nothing but this constant c. So this constant we can represent by writing 1. So that's why I wrote here derivative of this linear function is 1. Okay, rate of change of the linear function with respect to its the input is 1. That is straightforward for the linear function. But what about the activation 2 prime function here? What is this? Activation 2 prime is the linear function. What is this activation 1 prime then? So activation 1 prime will be the derivative of activation 1 function. So if you're using ReLU as activation 1, then the derivative of ReLU will be the activation 1 prime function. So we'll be defining another function, say ReLU prime, ReLU-prime. Okay, ReLU prime, and here say input is again z. Now what is the derivative of ReLU? Now see, derivative of ReLU is very much similar to the derivative of a linear function itself. Only thing is that we have to specify the derivative of ReLU is 1 if the output, if the input is greater than 0, otherwise it is 0. Okay, so basically what we want to do is, you see here, okay, this is important, you see, we want to compute the derivative of ReLU. We want to compute the derivative of the ReLU function, okay, derivative of ReLU. Now here we are giving g as the input. Now what basically this function is asking you is, what is the rate of change of this function? What is the rate of change of, not g, what is the rate of change of ReLU of z with respect to z? This is what we want to compute inside this derivative of ReLU function. Now what is here we can say now what it will be. If you see the ReLU function, it looks something like this. The ReLU function looks like this. You remember it, right? I mean, if the input, this is your z and this is ReLU of g. Now if the input is less than 0, output is 0, and if it is greater than 0, then it will be same as the input. Now, what is the derivative of this function? For this part, derivative is 1. For this part, derivative is 0. So it means here we can say that like if ReLU of z is greater than 0, if the output is greater than 0 here somewhere, then return 1. Otherwise return 0. Return 0. That is more or less the idea of the function derivative of ReLU. But in NumPy, we can write this entire statement in just one statement. Let's see how to write it. Okay, let's first compute what is ReLU of z. So let's say a is equal to, we're calling this function ReLU. We're calling this ReLU function here. First, we have to compute the output of this function ReLU, and then we'll be passing z to it. And then what we'll do is we'll write return, R-E-T-U-R, and return, and we will be passing 0 or 1. We have to pass, we have to output, right? So we can simply write it in this way: return z greater than 0. If z is greater than 0, then return 1, otherwise return 0. Not z here, return a greater than 0, because we want the output of the ReLU function. We want to compute the derivative of the output of the ReLU function, so we are doing it in this way. So that's all then. That is the ReLU prime. Now once we have these two functions ready, then we can write the code for these steps then. So let's see it. Now we want to compute DE2. These are straightforward thing now. O minus y multiplied by activation 2 prime of Z2. So we have to write here, what is O? O is A2 minus y. Y is y. So we have to multiply that thing by, this is a simple multiplication, multiply it by activation 2 prime of G2. So this is activation 2 prime, means the linear prime function of G2. Linear prime is written here. This is your linear prime. Okay, so let me copy the name so that I don't do mistake here. Linear prime of G2. Done. Now once this step is done, then we have to write db2. What is db2 then? db2 is same as de2. That step is also done. Now what is dw2? dw2 is equal to de2, which we have computed here, this de2 multiplied by a1 transpose. That is a matrix multiplication, so we'll be writing np dot and d2, and then here a1 transpose. Computing the transpose is easy, so we just have to write a1 dot transpose, t for transpose. So this will return us the transpose of this matrix a1. So done. This step is also done, and the next step is da1. So let's compute da1 is equal to w2 transpose dot de2. That is a matrix multiplication, so np dot then w2 dot transpose comma de2. de2 we have computed, so de2 done. Now we have to compute de1. Now de1 is equal to da1 multiplied by, this is a simple multiplication, da1 we already have computed, da1 multiplied by activation 1 prime. Activation 1 prime is nothing but the ReLU prime function that we have written, ReLU prime here. So ReLU prime is this function, and what we have to pass here is z1. Okay, let's pass z1. Okay, so I guess that's right. ReLU prime of z1, that's fine. And then we want to compute db1. db1 is equal to de1, which is already computed, done. And then we have to compute dw1. dw1 is equal to, it's a matrix multiplication again, so numpy dot and de1 is already computed, and we want a0 transpose, so a0 dot transpose. That's all we wanted to compute. And at the end, what we basically are interested in is, see here, why do we need to compute the gradients? As I have said you, we want to compute the gradients so that we can update the weights and the biases. So while updating the weights, our main goal is to computing the gradients of this b2, w2, w1 and b1. which are nothing but db2, dw2, db1, and dw1. So these 4 components we are interested in. So let's make our function return those 4 components. So return db1 comma dw1, or let's do it in this way: dw1 comma db1 comma dw2 comma db2. These are the rate of change of these weights and the biases with respect to the cost function, and that's what we want. Now see, one thing should be clear in our mind, that the sizes of these gradient matrices, that they should be same as the sizes of their corresponding initial value matrix. I mean, what you see here, dw1 is the gradient matrix for w1. So w1 size is same as dw1 size. It should be same. b1's size should be same as db1's size, like that. All these sizes should match. Okay, that will give us some hint that okay, things are going in the right direction. So let's see whether their sizes are matched or not. So let's make use of this function. Let's test this function, whether this compute gradient function is behaving expectedly or not. Okay, so in an expected way or not. Okay, so let's do that thing. How do we do that? So for that reason, what we'll do is, okay, let's copy this part of the code, the testing part that we did previously, and here write another block of code. Let's do it. First, we are creating this a0, then we are initializing or creating this w1, b1, b2. We are doing a forward pass, and then we want to do a like compute gradient steps. Say for example, we want to do this now: compute gradients of this a2, y, z2, a1, w1, z1. All these are there except this y. If now the thing is, what is this y? We know y is nothing but it is the ground truth. So it will come from training data at the end, but let's for the time being create this y by ourselves. Y is a numpy array. It should be say minus 0.5. The ground truth for this point will be minus 0.5, 0.5, reset 2 cross 1. All these are given: a2, y, z2, a1, w2, z1, and a0. Because you see here, this function will give us these weights and biases. This function will tell us what is z1, a1, z2, and a2. And then using these weights and the biases and z1, a1, z2, a2, this function will compute the gradient of all the weights and the biases. That's what this function will do. Okay, done. Now let's see whether the shapes are proper or not. Like at least that thing we can directly visually verify, no? So let's now see. We want like this thing is equal to this. That's what we want, right? So okay, let's do it here. So this thing is equal to this. What is dw1, db1, dw2, db2 will be whatever this function returns us. And let's now print them and see the shapes. Print dw1 this, and this. So dw1, then we want to compute db1, then dw2, and db2. Okay, let's print them and check it out. For that, let's execute this block of code to make sure that these are properly defined. Then let's say forward pass also. Let's define this function, and now let's test it. Now see, dw1 should be same. The size of dw1 should be same as size of w1. The w1 was our, now it is showing us like 10. Okay, here I have written 10, so let's make it 3 so that we can easily verify it. So we have 2 input neurons and 3 hidden layers neurons, and then 2 output neurons. So our w1 will be we need 3 rows and then we need 2 columns. So 3 cross 2, 3 rows, 2 column. And similarly, dw1 is also 3 rows, 2 column. b1 was like 3 rows, so here db1 is 3 rows. Then dw2 was 2 rows and 3 columns, so here also it is 2 rows, 3 column. And this is b2, 2 rows, and db2 also has these 2 rows. So these are the gradients of this dw1, db1, dw2, db2. These are the gradients of the weights and the biases with respect to the cost. Okay, once we have computed these gradients, then our computing gradient step is done. Now next task will be to compute the to update the weights and the biases. To update the weights and the biases, let's define a function. Define update weights and biases. And what are the inputs this function will need? It will need w1. See, we want to update w1, b1, w2, b2. So these are needed, and along with that, we need these gradient matrices also. dw1 corresponding gradient matrices, dw1, db1, like that. And also we need this constant there, which is known as the learning rate. So what are the inputs this function will take? It will take w1, b1, w2, b2, and their corresponding gradients, dw1 comma dw1 db1 dw2 db2. Along with that, we need to specify the learning rate eta. So, and then updating process is very simple. We just have to do this simple arithmetic operation. Say w1, this is the new w1, is equal to whatever the old w1 minus eta multiplied by, eta is a scalar, multiplied by the gradient matrix, so dw1. Similarly, we have to update all the other parameters, db1, dw2, db2. So w2, say this is b1, b1 will be old b1 minus eta db1. Similarly, this is say w2, so it is w2 minus eta into the old the gradient of w2, and this is b2 say, and then this is b2, then db2. Okay, so that's all. So w1 is old minus, this is old minus the eta into gradient of dw1, eta into gradient of db1. Okay, w2, okay, and b2. Okay, I guess that's right. Now that's all. Then once it is done, then we want it to return these new weights and biases. Say w1, b1, w2, b2. That's all. So that is the update weights and biases. Now once it is done, then we have written all these steps to perform this training operation. See here, we wrote the code for initialization, we wrote the code for forward propagation, computing the gradients, and updating the weights. Now what is the next thing that we have to do? Now we have to repeat. Once we compute these new weights and the biases, then we have to go back and we have to take a different training example, and then again you have to repeat this this process as many times as specified by the epoch. So now we need some training data. But before actually training the network for some real training data, let's try to train the network only for one training example. Let's see whether the network can learn one training example or not. So what we are going to do is we're going to consider only one training example, and then we are going to train the network only for that training example. We just want to see whether the network learns that single training example or not. If it is done, then in the next step, we'll do some real training. Okay, let's first consider the single training example. And this part of the code will be same as whatever we did previously to test these functions when we wrote them. So first, we'll be creating one training example of our own. Say input is 0.5, 0.5, the input x and y coordinate. And the output we want, the x coordinate should be negative 0.5, the y coordinate will remain same. That is the desired output. Now, once it is done, then the next step is initialization. So we would want our network to have, say, two input, two output, that is fixed, but this number of neurons in the intermediate layer, we can change it. Say, give it, say, enough number, say, for example, 10 neurons we want in the hidden layer. And after that, we'll do a forward pass, and then we'll compute the gradients, and then we'll update the weights and the biases. So what we'll do is we will call these update weights and biases, and we'll pass these values there. Okay, so update weights and biases, this w1, b1, w2, b2 already there, dw1, db1, dw2, db2, we have computed it using this function, and then eta we have to specify. Let's specify eta at the beginning itself. So eta is equal to, this is the learning rate. and usually it is set to 0.1 or 0.01 like that. Okay, so this is a hyperparameter. You have to set it from outside, and that is not something that network learns. The network only learns these weights and biases. Okay, so update weights and biases, and this will return the new weights and biases. So this will return these new weights and the biases. And that's all. I mean, yeah, that is one pass. Now we want to repeat this process. So we have computed these update biases done, and then we want to repeat this process as many times as specified by the epoch. So epoch is another one hyperparameter. So let's define it here. Epoch is equal to, say for example, let's let it go, say for example 20 times. We'll repeat this process 20 times, and there we have to write the loop. The initialization is done only once, and then this forward propagation, gradient computation, and update weight bias, this will be in the loop. Okay, so for, you can write I in range, say within a range of 0 to epoch. We want to compute, we want to repeat these steps. And now see one thing. After each epoch, since there is only one training example, what we will do is after each epoch, we will be computing the cost and we will display it on the screen. And let's see what I mean by this. See here. See, we have one training example. We do forward, compute gradient, update the weights. Again, we go back. We don't change the training example. It is still the same, but with new weights and biases, we will be again doing forward, compute gradient, and update weights and biases. Now, after each forward pass, see here, after each forward pass, what we can do is now we can display the cost. See, every forward pass should reduce the cost of the function. That should be, we should obtain that thing. And if everything is right, it should happen. So what we are going to do is now we are going to display the cost of the network after each iteration. Here also you can do, or we can display it here in forward propagation also. But let's do it here. Say we want to compute the cost. And what is the cost here? Cost is nothing but, how do we compute the cost? We are using the mean squared error as the cost function. And how do we compute mean squared error? It is the output generated by the network minus the desired output. We take the square of it. And when we do this, we perform it like component wise. See, O is a vector, Y is also a vector. So we'll be doing O0 minus Y0 square plus O1 minus Y1 square plus, like that we'll be doing. So this is the function for computing, or this is the formula for computing the cost. So that's what we want to do here. Cost is equal to, so we have to compute O minus Y. Now what is Y we know, and what is O? O is nothing but it is the activation 2. I mean, whatever it is A2, that is O. So we have this A2 computed here. So we can write like this. A2 minus, A2 is the output minus Y. We want to take the square of it. A2 minus Y square, that is power 2. And that's what we want. And A2 and Y both are NumPy arrays, so automatically it will be taken care of, like component wise part. And we want to compute the sum of it. So mp.sum of these matrix. I mean, this is a single column, so the sum of all the elements in that column. So A2 minus Y whole square, and we have to divide it by 2. So we can divide it by 2 just by multiplying it with 0.5 or dividing it by 2. So that is the cost. So at the end of each iteration, we want to say, for example, print the cost. So print the cost. And what we should expect is that every iteration, the cost should go to 0. The best that we can achieve is the cost is 0. And since we're training it only for one training example, I think it should go to 0. Let's see what happens. Okay, now we can execute it and see. Okay, it is showing me this function is not defined. I guess I didn't executed this. So for that reason, the error is coming. Let's re-execute and see. And the cost is 0.24 and it is going down to 0.14. I mean, you can see certainly it is decreasing, but it is not decreasing very fast, no? So what we do is, okay, let's increase the number of epochs here, say 20. and let's see 200, and let's see what happens. Now it is decreasing. It's like going very small, 0.004 and like that. And another thing that we can do is that since it is decreasing, but it is decreasing slowly, we can increase the learning rate by a magnitude of 10. Let's see now. Now it is now approximately 0, because 10 to the power minus 28, 3.69, it's like almost 0. So for one training example, it is working fine. Okay, let's now print the output there. So that will give us, okay, now it's working, something like that. So forward propagation, and this is the cost. And at the same time, let's print A2. A2 is the output itself, so we can print A2. So print A2 of whatever it is, A2 of 0, or directly we can print A2. A2 will contain we should get A2 equal to almost 0 minus 0.5, and now this is 0.5. Let's see. So A2 is, okay, here directly you are getting this direct result. This is A2, right? This is what we wanted, but at the beginning it would not be same, I guess. Okay, let's do one thing here. Let's reduce it to 20 and let's run this program once again. Now you can see A2 started with like minus point something, and Y component is also negative. But if you go down and down, you can see it is proceeding towards minus 0.5, and this is proceeding towards 0.5. But 20 epochs certainly not enough. So for that, let's make it say 100, and in 100 it will, I guess it will reach its destination. So it has reached its point. So for one training example, the network is working fine. I mean, we can at least train the network only for one training example. Now that's not the end, right? That is just the starting point. Now what we want is, we want to train the network to do reflection in general. With only one training example, certainly we cannot train it. So the first thing that we need is, we need some training data. Since we want to train the network to generate reflection of a given 2D point with respect to the y-axis, then what you can do is you can generate the training data. And how we're going to do this? Okay, let's first create a set of training input points. Okay, let's start step by step. Let's do it step by step. Say, for example, what we're going to do is, say, we have x underscore input, say, these are our input. These are going to be our input. We can do something like this: np dot random dot uniform within the range of -1 to +1. We are going to sample some points within the range of -1 to +1. And how many points, in what shape? We want it to be, say, 1000 row or 100 row, whatever the numbers of samples that you want. And how many columns? We want 2 columns. Basically, we want to sample 1000 two-dimensional point within the range of, or within the area -1 to +1. I mean, that square there. Okay, I guess you can see it now. Like if I print it, print x underscore input, you will see the values are something like this. Each row will be a 2D point. See here, each row is going to be a 2D point, and there will be 1000 rows. That's what this 1000 specifies. 1000 rows, each row will have 2 columns, and each of these values, I mean the values of that 1000 into 2 matrix, will be sampled from -1 to +1 using a uniform distribution. Okay, so that is our x input. Now, not only the input we want, we also want at the same time what are their corresponding output, what are the reflected points. Those also we want. Then how do we compute the reflected points? So yeah, to compute the reflection with respect to the y-axis is very simple. You just have to multiply the x component by -1. But then also the standard way of doing it is, now we can actually compute the reflection of all these input points just by multiplying this matrix with the reflection matrix. What I mean is, you see here, let me go through it very quickly. So this one we know, we can call it as reflection matrix here. Suppose you just see what I mean by this. Say 0.5 is the point for which we want to compute the reflection. Now see, if we multiply this 0.5 point with this reflection matrix, then what we're going to get is, we're going to get -0.5 and 0.5. You can think it of like this: -1 of this 0.5, 0 of nothing, that will give the x coordinate of the new point, and 0 of the x coordinate, the x component, y, the whole of the y component will give you the y component of the new point. But see here, 0.5, we want it to be minus 0.5, 0.5, this 0.5, we want it to remain same. So you can say like this is known as the reflection matrix. If you multiply this any to the point with this to the reflection matrix, then you are going to get the reflection with respect to the y-axis. Now the advantage of doing so is that you can compute the reflection of many points in the same go. See here, this reflection matrix, suppose now we want to compute the reflection of these 3 points, 0.5, 0.5, minus 0.22, and say this is 0.2, I guess, minus 0.22 and minus 0.2 and minus 0.1. So what we can do is we can simply make a matrix out of those 3 points, and then we can multiply that matrix with this reflection matrix. Then we'll get the reflection of all these input points there. Okay. Now one thing you see here, when we multiply these reflection matrix with these input points, you see the inputs are not written row wise, they are written column wise. See, this is the first input, this is the second point, this is the third point, like that. But in our case, you see, in our case, our inputs are written like this, 0.5, this way we have generated our input. So what we will be doing is that, see, we want to multiply with a matrix that looks something like this. And this matrix is nothing but the X input transpose. If we take the transpose, we will get this will become the first column, second column, third column, like that. And again, if you see the output generated by this matrix multiplication, it will get us the reflection points. But the thing is, each column will represent a point, but we want each row to represent a point. So whatever the reflection point we get after multiplication, we'll be taking the transpose of it to get the actual points there. So that is more or less is the story. Now let's write the code for it. So this is our X input. Now what we want to do is we want to compute the transpose. So sorry, we want to compute the the reflection points there. So what we'll be doing is we'll be okay. First, let's define the reflection matrix. Say reflection matrix is say Rm is equal to, it's a 2 cross 2 matrix. So here the first row is -1, 0, and for the second one we want 0 and 1 from the y. So that is our reflection matrix. And then what we want is we want to multiply that reflection. So numpy dot then this reflection matrix. Then we want this X transpose or X input, that whatever that X underscore input matrix, we want to take the transpose of it and we have to multiply it with this rotation matrix. That will give us the reflected points, but column wise. We want to take the again transpose of it directly. You can do it here. So that will be row wise reflected points. Now these are our, you can say like X underscore ground. These are the ground truth. These are the input and these are the desired output. Let's now see this desired output also. So print X and print this ground truth. So that should match. Sorry, I did a mistake here. This I want to put here. Let's run. So these are our input. So input is -0.4, 0.6. Then output should be 0.4, 0.6. Y coordinates, it will remain same. The X coordinate, the sign will be inverted. So if it is negative, it will become positive. And if it is positive 0.44, you can see it is now negative 0.44. And the Y coordinates sign, they remain unchanged. Here, see, you can see 0.71. It is still 0.71, but X coordinate was 0.8. Now here it is -0.8. Magnitude doesn't change, only the direction, the sign changes there. Okay, so these are reflected points. Now let's plot it. Let's see how does it look like. Okay, before actually putting them using them for training, let's plot them. So let me write another block of code here. So matplotlib is already imported, so directly you can plot it. So what do we want to plot? X input. Let's plot the this X input. So what we will do is we'll write pyplot as plot plt. I think it was sorry. So here, okay, to plot it, let's do it like this: plot dot scatter. Now let's plot these X inputs, X coordinate versus Y coordinate. X input of all the rows, we want all the rows, but we want the 0th column. That is our X points and the corresponding Y points here, comma. All the rows, but column 1. And let's give it a color. Color is equal to say red. These are our input data, training data. Okay, so plot.show, let's display it. Plot.show, let's display it. You can see these are the input points there. Okay, these are the points sampled for training. Now we want the corresponding output also, so let's plot the output also in green color. Okay, so in green color, let's plot it. Now not x input this time we want x ground. These are the ground root. Okay, let's say it in green color. You can see, but from here things are not very clear because there are lots of points, so don't do 1000 points, say just to see visually. We are generating 10 points, and then for 10 points we want to see the plot. These are the plots. Now you can see these red points are the input points and the green points are the ground truth. So is it so? Red point, green point, red, green, red, green. So if the red point is here, you can see, yes, it seems like yes, all of them are reflected. See, this with respect to y equal to 0, this right hand side part is the mirror image of the left hand side part, or left side is the mirror image of the right hand side part. So our training data is right. Now what we want to do is that we want these training data, so only 10 samples, I guess it will not be enough, so we'll be generating say 1000 or something like that, and then we'll train our network using these training examples. Okay, so let's do it. Now we want to train the network for all these training examples, right? We have these x input, say we have 1000 training examples, and we want to train the network for all these 1000 training examples. Now to do that, let's start from here. I'll copy this part of the code. Let's paste it here. This was only for one training example. See here, a0 and y, that a0 was always the same training example, y is the same, the corresponding output, and then we initialized it, and then we repeated this process for as many times as the number of epoch. Now what we want is inside this epoch, like for each iteration in a single epoch, we want to train the network for all the training examples. Okay, so what we'll be doing is we'll be writing another loop here for j in. Now how many training examples we have? We have 1000 training example. For the time being, let's write it directly for j in range, say 1000, because we know we have 1000 training examples, so 1000. And for each of them, now what we want to do is we want to change these a0 and y. In each iteration, we want to take a different a0, we want to take a different y for each training example. And now let me do this thing. Yeah, okay. Now we don't want this a0 and y to be fixed, so we want to take, in each iteration we want to take one example at a time. So see here, our examples are there in x input, but they're in row wise, but when we give the input, we have to give the input column wise, right? So what we'll be doing is, you can say like a0 is x underscore input, okay. Of that, we want the z row, so z row and all the columns, but we want to transpose it, because we have these components row wise, each row is a point, but when we give the input, we want to give it like a column vector, so we're taking the transpose. I guess you got the point. And y is also the same thing, but it is not from x input, it is from the ground truth. J and transpose. That's done. And the cost here, the rest of the things are same. We'll be doing the forward propagation, we'll be computing the gradients, we'll be updating the weights and the biases, and then we want to take the next example. But before taking the next example, we want to accumulate the cost also. And you see, we are not going to print the cost for each training example, rather we'll be printing the cost at the end of each epoch. So here, let's define a function, define a variable, let's say cost is equal to 0. And here, instead of writing cost equal to something, we'll be writing cost is equal to cost plus whatever the cost of the current training example will only accumulate. And after that, once it is done, once this entire for loop, this training is done, we'll be printing the the cost at the end of each epoch. Okay, so that's all that we want to do. Let's run the code and check the thing. So it is showing me an error. Operation could not be broadcast together. 2 cross 10, 2 cross 1. There is a problem here. Where could be the problem? X0 dot transpose. Do I have to do a reshape here? So it's 2 cross 1 we want. So let's do it. Let's do it. Index 10 is out of bounds of x is 0 of size 10. What is size 10? Okay, I'm getting some errors here now. Where could be the problem? Let's run this. 1000 points we have, and then we want these 1000 points to go properly. Now it's going fine, I guess. Now it's doing, see here, we can see the cost is going down and down and down and down. See here, it is 10 to the power minus 5 now. At the end, it stops at 10 to the power minus 6. So at each epoch, now our cost is going down. It means our network has learned something, but we want to test now. And since it is doing reflection, we can test it visually, right? So for that reason, let's first create some test data, and we'll be creating the test data very simple. So we'll do some fun here again. Let's see what we are going to do. So what we'll do is, see, first we'll give, if the network has learned everything properly, learned how to generate the reflection, then we'll give the network a set of points like this. So this is actually, you can think it of like it is y is equal to x squared card. So we'll be sampling some x points, and then we'll be computing y equal to x squared. So these points will give the network as input, and if the network has learned everything properly, then the network should give us this other part. The reflection part should be symmetric, so we should see that bowl there. Got it? So let's now try to do that. Okay, let's sample a set of x's there. So let's say x underscore, or let's call it a test, test underscore x is equal to numpy dot a range will work within the range of, say, 0 to, we want the on the right hand side of this 0 axis, 0 to 1, with a step size at 0.1. Okay, or 0.01. So as many points we want, we can take. Say we have these points, then we want the corresponding y also. So test underscore y is equal to x squared we want to use. So it is now test underscore x squared. So that is our test data. This is what we're going to give as input to the network. Let's first plot this test data. Let's see how does it look like. So we'll be writing another block of code here, and we'll be plotting it. So by plot.plot, so plot dot scatter x versus y. Our x's are test x, this is the thing, and y is test y. Okay, so these are our input, these are going to be our input points. And let's see now how our input looks like. Plot dot show, and that's all. And then let's run this block of code, and see, this is our y is equal to x squared. So we took very little points. So here, let's say it is 0.01. So 100 points now, I guess. Now run. So these are the 100 points. So now see, if we give this part, then the other part should be computed by the neural network. So let's try to do it. Now what we want is, for each of these these points, now we want these points, and we want to give these points. For each of these points, we want the network to compute the corresponding the output there. So for that reason, what we'll do is, we will put it in this way. So we'll first create the inputs. So for that reason, what we'll do is, we'll say, for example, like, let's call it a test. The test is equal to numpy dot column. There's a function column stack, umn underscore stack, right? Yeah, column stack. This will do what you see here. See, right now our x and y, they are two different arrays there. So we want to combine them together to make it as a set of points like that. So what we'll do is, we'll write this test, say this here, comma, this y there, this x coordinate and the y coordinate will put together, will make a point. Like now each row of test will represent a point there. Okay, so let's run this block of code and see here each row of this. Say for example, if I print this test, you will see it will be, so each row now is a, each row is now a point here. This is one point there, another point there. These are some points there. Why is it so? Oh, it is y equal to x squared. Okay, no problem. These are some points. Each row represents, this is your x coordinate, y coordinate, x coordinate, y coordinate, x coordinate, y coordinate. Now for each of these points, now we want our network to generate the reflected points. Okay, so let's see how the network does that. So for that reason, it means what? We want now the network to predict. We'll give this thing as input and we'll ask the network to generate the output. Now, see, this time when we ask the network to generate the output, we are not going to update the weights and biases. Now the training phase is over. After training, now whatever it is the current weights and biases the network has, based on that, we want to know what is the final output. Okay. So for that reason, what we'll do is now, okay, this plotting is done. Now here, let's write another block of code. Okay, not here. Let's do it somewhere else. Let's do it here. Okay, now here what we'll do is for each of these examples. So for I in range, then we don't know how many test datas are there. So here we can do one thing actually. Test dot shape or test dot shape. It gives you the shape, and of that we want how many rows and how many columns there. So as many rows are there. So this is your the zeroth component. Let's first see what is this test. If we print this, let's see. Before writing this, let's print this thing. Okay, let's print this. It should print you as many rows are there in test. Tuple object is not callable. What am I doing here? Here, okay, 100 examples are there. So yeah, there are 100 points there, right? So 100 examples. So this is actually the number of test data that we have. Okay, so what we do is for now, let's then store this thing somewhere so we can use it later on. N is equal to this. Now for I in range, say 0 to n. So for each of them, what we want to do is now we want to get the output now. And how do we get the output? We have to actually compute the forward propagation, this forward propagation step, forward prop step here, forward prop with these weights and the biases, and whatever it is A2, that is the output. So directly we can call forward prop. Okay, so for this, first let's compute this A0. What is A0? A0 will be, now see again our test data is row wise, so we'll be taking test data, then the ith row, and we want to take all the columns, and then we want to take the transpose, then we want to reshape it to 2 cross 1. This is our A0. Now we want to do a forward pass, forward prop here. Okay, and we want to specify now we want to specify this W1 B1 W2 B2, the current weights and the current biases there. So let's do it here this way. So now forward prop, and here what we want to do is A0 W1 B1 W2 B2. Now what this W1 B1 W2 B2 will be, since when we train the network, you see for each 100 epoch we are computing, we are updating these weights and these biases, initialize these weights and biases. These are now accessible. This W1 B1 W2 B2, it will be accessible from here also. So we can write, now these are the final weights and biases. With this final weights and biases, we want to do forward propagation. See here, when we do forward propagation, we do not change anything about the weights and the biases. Okay, we just want to compute the forward propagation, that's all. And the results will be stored in A1. Let's store the result in the same way it returns us like forward propagation, where it is this way. So this. So now here we'll be writing this is equal to this, and out of these we are interested only in A2, so we'll be printing print. Okay, let's print this A2 and see. So A2 shows us some of the points, but verifying A2 that way will be difficult. So we'll be doing something like, okay, let's do something like this. Let's store the X, we'll visually verify it. Okay, so for that reason, what we'll do is in X, we'll be creating a blank list to store the X coordinate or X coordinates of the reflected point. Similarly, we'll create another blank list that to store the Y coordinates of the reflected point. And then we don't want to print it now. What rather we want to do is O underscore X dot append. And there we want A2 is the final output of A2, the 0th row. Only 2 rows will be there. The 0th row, 0th column. 2 rows, 1 column will be there in A2. So 0th row, 0th column will become the X coordinate. And 0th row, first column will only 1 column is there, but 2 rows are there. The first row and the 0th column will become the Y coordinate. Why is it so? You see, the output generated is this. Here, this is the output. So it has 2 rows. This is the 0th row, 0th column, and this is the first row, 0th column. 2 rows, 1 column. That's why the 0th row, 0th column is the X coordinate, and the first row, 0th column is the Y coordinate of the reflected point or of the generated points. So let's see now. So that's what we are doing here. So now once we do that, what we can do is now, since all the outputs are there in OX and OY, now we can we can compute it, and then we can plot a graph of it. So let's do it. Let's create another block of code and then write plot dot scatter and O underscore X versus O underscore Y. That is the output that we want. We want to see the output now visually, and say color is equal to, say, blue. Lowercase will work, I guess. And then plot dot show, say plot dot show. And let's see. Okay, the blue curve is coming, but okay, let's plot the the input data also. That will show us how good it has learned the thing. If it is properly symmetric, then everything is fine. Okay, let's now plot the same thing, but for the input data. Input is there in test data, so test plot dot this test. Now test all the rows of the 0th column. 0th column of all the rows represents the X. Similarly, 0th column of all the rows, but we want the first column, the Y, and colors should be, say, for example, red. Red is our input and blue is the output generated by the network. And if red and blue, they are properly symmetric, then we can say that the network has learned the thing. Now see, it seems like they are properly symmetric now. So it means we can say that the network has learned the thing. At least visually we can verify. Now, since up to this point things are working, now it is time to give the network the input that I showed you at the beginning, the half of the phase. And that half of the phase is actually there in a CSV file. Let me first load that half of the phase, and then we'll proceed further. Okay, now the half of the phase dataset is there in my Google Drive, and I'll be sharing I'll be uploading the file in GitHub. From GitHub, you can download it, you can store it in your drive, and then from there you can read it. Okay, so it is stored in my drive, and inside my drive I have a file called file.csv. This is the file that contains the X and Y coordinate of the of the points there in that training in that test data. And then this is how we load these. We connect with the drive, and then from the drive, using this pandas library, now I'm reading that CSV file whose name is file.csv. Okay, this block of code I just copied and pasted. So let's see. This is just the reading part. Okay, so we are connecting with the drive, so it might ask you for permission. So you allow, and let's see. Okay. Okay, the mounted is done. Now we'll be importing this file.csv. It is read. Now let's see what that file.csv is. So if you see the size of, okay, it is red here. So let's make another block of code. The file is red and it is stored in xtest now. So let's print the shape of xtest. Okay, print xtest dot shape. Okay, and let's run it. It'll tell you that 18,100 rows are there, 2 columns are there. 2 columns because that is the file that contains some 2D points there. So 18,154 2D points are there in xtest. Okay, let's now plot this xtest using matplotlib. So how do we do that? So let's plot it. Plot dot scatter, CATT or scatter, and then the x coordinates and the y coordinates. Xtest of all the rows, and the 0th column will be the x coordinate, and all the rows and the first column will be the y coordinate. And then we want the color to be, say, red color, I guess we used for training data. So here, what is the problem? 0 is a decimal integer. What is that? Is it this? Okay, let's see. Okay, it's done. Now the image looks like blurry because see here, each pixel is drawn, like each point is drawn with this big circle there. You can specify the size here. Size is equal to 0.1, and that way it will look much cleaner. Now you see, with size equal to 1, we get this. But anyhow, that is just the drawing part. Now what this xtest contains, it contains 18,000 two-dimensional point, and if we plot those two-dimensional points, x coordinate versus y coordinate, it will look like a face. Now what we want is, we want to give these 18,154 points as an input to the trained network, and we can ask the network to give us the reflected points. Now if everything is fine, then the reflected points should complete this face. The other half should be accurately symmetric with this right hand side part of the face. Okay, so let's try that thing. So what we're going to do is, now we are going to give this xtest, all the points which are there in xtest, we're going to give as the input to the network. And it is same as what we did with this test data. Like our test data was this, and then we pass this test data through the network this way. That is how we compute it, right? So the same block of code basically we have to write here. So I'm copying it and I'm doing it like this. So here only thing is that instead of test, it is xtest. This is xtest, and that's all. This will do the job. Okay, done. Now we want to plot the xtest versus the input data. Same thing, same plotting will be done. So I'm just copying it from here, and I will create another block of code. I'll be pasting it here. O.x, O.y blue, scatter. Now not test, we have to do the scatter plot of xtest. And also, since we have seen this size problem there, let's specify the size also. Size equal to 0.1, and here also size is equal to 0.1. Now let's run this block of code and see what phase it gives us. Oh, that's nice. Now see here, for each of these red pixels, so I'm drawing it red. Initially I said it will be orange, but anyhow, each of these red pixels, these are the input points there, and for each of these red pixels, the network has generated 1 blue pixels. And since it has learned properly how to generate the reflection, we can see as a whole, if we give half of the face, then it returns us the other half of the face. Okay, so that's why you see this symmetric face there. And that's all that I said you at the beginning that we'll be doing, right? So what we did is we just build a neural network from scratch. We write the code of a neural network from scratch, and then we saw how we can train the network and how we can make use of the network to do some meaningful tasks. I'll upload this code in GitHub. From there you can download, and also I'll upload this file.csv in GitHub. So what you can do is you can download this file and you can store it in your drive, and then you just execute this code as it is. It will work. Okay guys, then that much only in this video. Hope you people have enjoyed the video, you people have learned something from the video, and importantly, if you like the video at any moment of time, please don't forget to like the video. And if you're interested in contents like this, then please subscribe the channel. Okay guys, then that much only in this part of the video. See you guys with some new content in the next video. Till then, have a nice day.